All right. So if I had a circuit simulator, all right, so you get this is Simulink. This is actually a simulation tool within MATLAB, which is really commonly used for control purposes. Right. So if I'm designing a control system, I'll use this kind of a thing. Okay. Now this is it's a circuit simulator. It's an RC circuit. What I have in this picture is basically a voltage source, which has square waves, and then I'm measuring the voltage across that capacitor. And what I see is basically, you know, I see that my voltages are 5. So this guy here is probably 5 minus 5 e to the negative t over tau, or whatever, you know, and then this guy here would be 5 e to the negative t over tau. It's just repeating like that, right? So how does a circuit simulator know how to solve for the voltage? How does it know how to get that? What's that? How would you do it? Not sure what you mean by area under the curve. How would you figure out? I think I kind of know where you're going with that, maybe, but it means, in other words, it doesn't guess a particular solution, does it? That sounds like artificial intelligence. That's not. That doesn't. In other words, it doesn't. So exact solutions aren't what computers do. All right, it's impractical to do it that way. The computer needs a numeric way of approaching this. All right. In other words, and computers don't ever deal with t. Right. What is t? If I say the voltage here is 5 minus 5 e to the negative t over tau, what kind of number is t? Real number, imaginary number? What kind of number do I have? Real number, right? In other words, a computer can never have real numbers, right? Why can't it? Why can't I have real numbers? Well, I mean, yeah, fundamentally, I'm limited by the number of bits, the number of values that I can really represent. So yeah, I have binary numbers, you know, or some number of bits, right? So I can't have, you know, infinite precision that comes with real numbers. So I got a problem. All right, so we're going to make that jump to what happens inside of a computer when it's processing this kind of a thing. So if I was going to develop a circuit simulator, what would I need to do? And this approach isn't just useful for, say, circuit simulation. This would be useful if, let's say, I wanted to do a control system. So if I had a microcontroller, if I was doing an embedded system and I was trying to control something, I would want to use the exact same type of approach that I'm using here, which is to say that I would want to know the values at individual times to use them for some kind of prediction in my control system. All right. So let's say I wanted to graph that function right there, right? So this function is a continuous function of a real variable t. All right. Now, if I tell you that you know, I want you to make a graph of that thing, all right? How have we done that? So there's sort of a couple of steps that we've taken to graph this, right? If I want to draw a graph of this, let's say from t equals 0 and t equals 0 to, I'm going to say t equal to 7 times tau. Why did I say 7 times tau? Where did I come up with that? Just off the top of my head. Yeah, so you probably heard from Yahoo, right? If I have an exponential like this, you know, after about 5 tau, you started to get basically the exponential is kind of gone. So I did a little bit more than that. Okay. So 7 tau is what I chose. Now, if I choose a starting point, I choose an endpoint. Now, for you guys to draw a graph of that in MATLAB or in any computer program, this isn't necessarily just tied to MATLAB. The specifics of the syntax are for MATLAB, but how would you do this? If I told you to do it like that, it'd be a row vector. So you define a set of times, right? And I don't know, what would I do here? I'd have some increment, which I'm going to call delta t. All right, and I would stop it at my endpoint 7 tau, like that. Okay. So really what I've kind of done here is I've said, you know what, am I plotting this at all the values of time when I do this? No, not at all, right? I'm plotting it only at some values and I have an increment here. Now that means that what am I really plotting? I'm not plotting x of t, but I'm kind of plotting an approximation to x of t, right? Why do I have to do that? Why can't I plot x of t? I want to see x of t. I kill the computer, yeah, because how many real I mean, just between 0 and 7 tau, how many real numbers exist? No, well, not just a lot. I mean, infinite. There's an infinite number of real numbers, infinitely many real numbers between 0 and 7 tau. All right, so it's not possible. The computer would crash before you could ever do it, right? So what we have to do is we say, all right, we're going to make a reasonable guess as to how big of a jump we should make between points, and then just plot at those points. Okay, so really, this is the way that I kind of set up the code here a little bit, right? So, in this case, what I did was I said, all right, I'm going to make a jump delta t, an increment value. Now notice what I did here. It's a little bit different than what I wrote on the previous slide, where I defined a time vector t, and I defined this vector here called n. Okay, so n equals 0 in steps of 1 to 600. Okay, so what would t look like here? So my t is delta t times n. So what would that, if I had to just sort of think about what the values are going to be there, and just expand it a little bit, what's the first value that would be in that vector? 0. What's the second one? Delta t. What's the next one? 2 delta t. And it would keep going until it got to what? 600 delta t. Okay. So the way to kind of think about this, or the way that I think about this, is I can think about my values sort of in two different ways, right? So so I'm plotting out just in Excel. I wrote so for n equals 0, I get t equals 0, and x of t equals, I just plug in that value of time. For n equals 1, I get this value of t, and I get that value of x of t, right? So they all kind of go together. Now this array here is something I can hold in memory somewhere in a computer, right? So it's like what I have here when I look at this, right, is each of the values in the time vector is some integer number n times delta t. So I could plug that in to this function, couldn't I, to say that's what I really am plotting. So I could say that I have 5 minus 5 times e to the negative n delta t over 0.1. Now, if I do it like that, right, what's that a function of now? Is that a function of time? Or is that a function of a real number? It's not a function of a real number now, right? What's it a function of? When I say it's a function of something, right, it means that I have some independent variable, right? Here, t is the independent variable. X depends on it. What is x? What is this guy down here? I basically plugged in t equal n delta t into this expression, and I got this. What's that a function of now? It's not a function of t anymore, right? Function of n. And what's n? This guy was a real number. What's n? If I want to be real exact with this, I guess it's a whole number, but I'll call it an integer. Right? Right? It's a function of an integer. And this is kind of a nice way of thinking about things in terms of the way a computer thinks of it, right? So it's like the 0th entry in x, the first entry in x, the second entry in x, so on and so forth, right? So this guy right here is that we're going to make a distinction between these two. This, when I have this guy as a sort of a function of a real number, sometimes what I do is I call this a continuous time function. All right. It is how x of t exists in the real world, right? If I had an RC circuit, that's what x of t, and that x of t was a voltage, that's what that x of t would look like. This, I call that discrete time. Now, what the heck does the word discrete mean? If you looked it up, what would it? Yeah, basically discrete means like separate or distinct, right? So what it means is I've got separate, very distinct values of time. So at delta t, 2 delta t, 3 delta t, 4 delta t, not all the times that are possible, but at very discrete, sort of distinct values, okay? So we make this distinction here where I call this, so a continuous time function versus a discrete time function. A discrete time function is basically a function of some integer variable n, all right? And it really represents how a continuous time function is stored in computer memory, right? As an array of numbers. All right, now you're going to learn a lot more later on about discrete time, but it's important to understand this because it's a concept that you haven't formally ever thought about, but you'll kind of understand at some level because you've been using it, all right? Because every time you make a graph, that's what you're effectively plotting, right? So one way of looking at this here, right? So I plotted x of t and x of n, okay? Those look the same, don't they, those two graphs? What's the difference in my two graphs? What's that? Yeah, well, yeah, the x-axis is different here, right? So, and I labeled these differently. So on the top there, I can see this guy is time in seconds. What's this? Sample number. So what I did was I said I got 0 point, 1 point, 2 point, 3. So I basically plotted here x of n. I'm plotting my independent variable, sorry here. My independent variable is n. And this is t. Now, it's hard, kind of like what units do I give to n? They're just integers, 0, 1, 2, 3. So I tend to call those sample numbers, right? Because it's basically the number of the sample. Now, that's a new term. What do I mean by sample? Well, I got to be careful. Basically, what I'm saying is if I had the true continuous time function, I'm picking off values at certain points or sampling that thing, right? So if I had an analog to digital converter, what that does is it samples at very fixed times, right? So at some level, really what we're doing is we're kind of building an analog to digital converter here, right? It is really kind of what we're doing, okay? Now, this is important if I want to think about doing stuff numerically, right? All right, fundamentally, this should be a pretty easy concept. Again, you can make it more complicated for sure, but hopefully the basic idea makes sense. These two graphs are the same, but they mean something different because my x-axis is totally labeled different, right? It is important what your x-axis is labeled always, because it can mean something totally different if my x-axis isn't labeled right, okay? All right, questions about that? All right, so now, right, so I need to be able to use that here, right? So there's got to be a simpler way to build this piece of software, right? To build this circuit simulation. There is no way that I'm using some kind of AI to guess the particular solution and all that kind of stuff, right? So I'm not going through my 3 steps of my homogeneous, non-homogeneous, all that sort of stuff. That's not happening. There is a simpler way to do it. So to think about it, we got to go back to the definition of the derivative, right? So you learned this way back when in calculus, which wasn't, I say way back when, it wasn't way back when. You're gonna be like, oh, this is so long ago. It was 6 months ago. It was, yeah, 2 years, long time. I'll tell you, it was 25 years ago for me. So this thing here, right? What the heck is that? The instantaneous rate of change, good term. So when I look at this, okay, forgetting anything on this, what is a derivative? So it's a rate of change. It's a slope. Yeah, it's a slope, right? So if I gave you a line, right, you learned in algebra that if I gave you a line and I said this was y and this was x, and you said this guy had a slope m, how'd you calculate that? rise over run, right? So you did delta y over delta x, right? Where you basically said, all right, over this point right here, this was delta x, that distance, and this distance is delta y, right? So now if I have a function that's not straight, right? If I got a function like this guy, this blue guy here that's curved, right? You basically say, well, I take 2 points, and what I do is I say those 2 points, first one is at a time. So first of all, let's be careful. I'm saying this is y of t that I've graphed. So the blue line here is a function y. And I'm basically saying at time t, it has a value y of t. And then at sometime delta t later, right? So t plus delta t, it's got a value of y of t plus delta t. So if I just said, all right, I want to calculate the slope, knowing that I have this delta t and this, so this is my run. My rise would be y of t plus delta t minus y of t, right? This is my rise. This is my run. And I just calculate my slope by saying rise over run, right? What the heck is this limit as delta t goes to 0 crap? Yeah, it's saying basically shrink delta t down until I get to the point where basically it's so small that I'm basically just calculating the slope of a line right at that point. All right. Newton had to do that. Why did Newton have to do that? Because he didn't have a computer, right? So Newton's to blame for coming up with the fact, well, if I plug into this, a times t to the n, and you go through and you do a proof, you find out the derivative is n times a t n minus 1. Fundamentally, this is what we still teach you all the time, but you don't need to ever do it because the computer could do it for you. All right. And when I say computer can do it for you, not in the sense that the computer could symbolically do it for you, right? But how would I get a computer to try to do this? What would be your basic guess for trying to get a computer to calculate a derivative from data? And that's a very common thing to do in controls, right? If I'm making a control system, let's say I want to control the speed of a motor, for instance. Some of you guys may have heard of a PID controller, right? So I might want to compute a derivative, right? So how would I do that? How would I compute a derivative? How do you think you would do it?
Points that are a very small distance away.
Take 2 points that are a very small distance away from each other. And the question is, how basically can I take Newton, so dy by dt equal to the limit as t goes to 0, and say, you know what? If delta t is small enough, and that's going to be the bane of your existence, is what is small enough, right? It's actually not that hard, but it's I know it's hard for people to get their mind around at first. If delta t is small enough, y of t plus delta t minus y of t, this guy here, basically what this means is I can take 2 points that are close enough together, take the difference between them and divide by the time step. So this delta t, sometimes I'm going to call this the time step. And when I use that term time step, I mean it to refer to the fact that it's how much I step it forward in time as I move from one point to the next. Okay. So that approximation should basically be almost true, right? So I'm getting rid of the limit. So I'm not going to get a closed form solution like Newton liked, but I'm going to get one that works for the computer. Okay. So how do I do that? Well, basically what I end up saying is that and this is a term I'm going to use here. I'm going to say I'm discretizing the equation. I'm taking it from, so I'm converting it. So yeah, I'm uncontinuousing it, if that's a word, right? Discretizing is better than, you may not like discretizing, but it's better than uncontinuousing. Is I'm taking this guy and I'm saying somehow that dy by dt can be approximated by this pretty simple piece of math that you learned in algebra. Because if I look at this, what this is, dy by dt, this side of the equation here is calculus. What's this side of the equation? Algebra. Right. So the computer doesn't ever do calculus per se, right? It's actually doing algebra. All right. And now our goal again, like I said, is to make sure that delta t is small enough that that approximation is good. All right. So we got to talk about what that would mean. So, all right, let's say I've got this circuit. All right. And I said to you, all right, so y of t is gonna be the voltage on that capacitor, x of t is my source. All right. And what I want to do is I want to solve for y of t, and I want to do it in discrete time. All right. I want to do it numerically. So how would I approach that problem, do you think? How would I approach converting this into a problem I could solve numerically? Well, what did we say was the key? Dy by dt is what? Well, I go back to my definition here, right? That, right? So basically, yeah. And, you know, you can work out the details of the math, but you should don't pattern match to this too much. Don't worry about that. Basically, if I look at this, what do I have? I have a rise over a run. Okay. Basically, the difference in how much I go up vertically over how much I'm going over horizontally. Right. So I'm basically going to say, all right, I want to convert this guy. What I'm going to say is I discretize it. So I'm going to convert this into tau. So just here's my equation here, and I'm going to plug in tau. Oops. I want me to. I confused it. What's that? What are you doing? Yeah, yeah. What's going on? Okay. Come on. Okay. All right. Hopefully this will work. There we go. All right. So I replace that dy by dt with y, oops, y of t plus delta t minus y of t all over delta t plus y of t equals x of t. Like that. Okay. Now, this is an algebra problem. Okay. So if you think about this at time t equal to 0, what's always true? If I want you to solve a differential equation, what's always true? What do I always have to give you? Initial condition. So I give you y of 0. I have to give you that. So if you think about it, what else do I have to give you? Well, I have to give you whatever the input is, x of t, right? So the input's going to be a step function, or it's going to be a sine wave or whatever. So you're always going to know x of t, and you're always going to know y of 0. Okay. What do you not know? Well, I wouldn't know y at time t plus delta t. Right? So let's think about it. At t equal to 0, let's think about what I know. At t equal to 0, I would know x of 0 because I would have to give you an input. Right? I would know y of 0 because I have to give you an initial condition. What I will not know at that time is y of 0 plus delta t, or just y of delta t, like that. And if I look at this, right, if t was equal to 0, so if t equals 0, I would have tau times y of t plus delta t. Oops, let me plug in t equals 0. Delta t minus y of 0 all over delta t plus y of 0 equals x of 0. what can I do? Well, the only thing so again, I'd have to be given a number tau. We're going to use an example here in a minute where there's numbers. I have to choose a delta t, so I'd have a number for that. I know what the input would be at that time. I know what the output is at that time. The only thing here I don't know is what? What would be the only thing I wouldn't know? Y of delta t. Basically, what I don't know is the value of y in the future. That's what this is saying. At time t equal to 0, I know what the input is because that's what time it is right now. I was given this, but I don't know the future value. So I can solve for that future value, though, can I? Just by doing some algebra here, right? I can just rearrange this whole equation, do some algebra for myself, and solve for it. And I think I want to do that without actually walking you through all those steps. I'm going to try to do this in my head real quick. X of 0 times delta t over tau plus delta t. I should be 1 minus delta t over tau times y of 0. All right. In other words, if I tried to rearrange this thing and solve it, you don't need to sit and watch me go through the algebra on that. That's basically what it works out to be. Now, if I look at that, that does have some meanings. I want to look at it like this for a second. X of 0 times some number. I'm going to call it A1, or am I? I am. And some number times y of 0. Okay. That I like that in a way because I can look at that and I can say, well, this actually makes the differential equation make a little bit more sense to me at some level. Because I can look at this and I can say the future value of the output. So if I'm thinking about the voltage on a capacitor, I'm saying the value of that capacitor a little while from now is related to the input right now and the output right now. Okay. So in other words, that's basically what I'm seeing here is that this differential equation is kind of telling me something about the memory of that system. That somehow this guy remembers the past. So in the future, the value of the voltage is going to depend on what the voltage is right now. And if I hadn't plugged in a specific time, I could have just said that y of t plus delta t is just simply A1 times X of t plus A2 times Y of t. And that's basically this is just algebra, right? If I think about what's going to happen here with this whole thing, right? This tells me right here, right? So if the time right now is t, then the output y at the time t plus delta t depends on the input right now and the output right now. So if you think about what's going to happen, right? So if I think about this circuit, let's say this X of t was 4 U of t. In other words, at time t equal to 0, I flip the 4-volt battery on. What's going to happen to the voltage across this thing, across that capacitor? What's going to be its final value? 4, right? So what this says is eventually, and of course, you know what it's going to do is it's going to ramp up over time like this, right? So initially, when the value is starting out at 0, let's say, and it's rising up, the value at the next time is going to be a little bit bigger because it depends on the input and the output. But as I get farther along, what's going to happen? As I get farther along, you know it's the case that the input and the output begin to get equal to each other, right? And so effectively, what we begin to see is that the two of them should start to sort of even out on us. Okay, all right. So bottom line is I can use this thing now as sort of an expression. So y of t plus delta t equals A1 times X of t plus A2 times Y of t. Okay. Now, what I can do with this is I can say, all right, well, at t equal to 0, or n equal to 0, I can calculate y of delta t. So I plug in t equal to 0, and I get y of delta t is equal to a1 x of 0 plus a2 y of 0. What am I going to get at 2 delta t? What's that going to be? When time t equals delta t, I'm getting, right, delta t plus delta t. So I get y of 2 delta t. What's that going to be equal to? So when the time equals delta t, I plug that in here to my t value, right? So I get a1 times what? X of delta t plus a2 times y of delta t. At 3 delta t, what am I getting? What do I get at 3 delta t? It's going to be a1 times what? X of 2 delta t plus a2 times y of 2 delta t. So what I'm saying is, yeah, it's a recursion, right? I'm basically saying, yes.
Never mind.
Yeah.
I was gonna say, remind me.
Yeah, so it's basically, well, so discrete time, discrete math, right? This is the same concepts that are all tied in here, right? So I'm saying that the output at the next time step is always related to the input at the current time step plus some weighted version of the output at that time step. And I can basically, at each time step, I can always predict what the output's going to be one time step later. Now, we can generalize that a little bit here, but what does that look well set up to do? I mean, if I wanted to compute this in the computer, this is the kind of thing that looping is well set up to do, right? I can set up a for loop that basically just keeps walking me through to say, all right, well, at the next time step, I can basically just calculate based on whatever values I currently have. So this is perfectly set up for a looping situation. All right. So if I try to generalize this, right? If I know that my values are spaced at n times delta t, I can look at this thing here and say, in general, that should say n delta t. At t equal to n delta t, yeah, at t equal to n delta t, let me just, y of delta t times n plus delta t. I have that expression. Okay. Now I can factor out a delta t over here, right? I can say I have y of n plus 1 delta t equals a1 times x of n delta t plus a2 times y of n delta t. Now let's look at that for a second. What is that? Okay, I always want to pause and look to say I should be able to make sense of this in words, right? What I'm saying is y at the next point is equal to sort of the weighted combination of x at the current point plus y at the current point. So when I look at that, do I even need the delta t? No, I don't. I could just get rid of it. And I could say y of n plus 1 is a1 of x of n plus a2 y of n. Now that's a complete discrete time relationship now. And it's super easy for me to work with, right? So let's apply that to a real example and see how we can use it to try to solve, right? So I got an RC circuit here. All right. Now, I've said that my input is 4u of t. So that's my x of t. And y of 0, I didn't put the number here, but in my example, I used 10. So I say it starts at 10. Now, before I do anything, I want you to tell me, because you should know, what does y of t look like? If I said y of 0 is equal to 10, and I applied 4 volts, you should be able to tell me what y of t is going to look like. Where's it start and where's it end? And what's it look in between? If I were to draw the graph,
So it's starting at 10 volts.
starts at 10, decays to what?
X.
Yeah, which I've said is 4 u of t. So it's going to decay to 4. And what's it going to look like? So it's going to start at 10, it's going to end at 4. What's it going to look like in between? Like an exponential. All right. At the end of the day, what you need to be able to understand is intuitively, okay, if I get a first order circuit, I should know what the output's going to look like. You don't usually care all that much about the details of it, but you should be able to figure out what is it going to look like intuitively. It's going to be an exponential, and you should know where it starts and where it ends. And at what point does it kind of level off here? Well, it levels off at 4, and at about 5, 6 tau is where it's flattened off, right? That's how much time it takes for it to reach 4. Okay. So I know what that looks like. So I want that picture in my head because that's what I want this graph to look like, probably. All right. Now, I can go through this whole thing here and I can discretize this equation, and I can basically say, all right, I know that y of 0 is equal to 10. And I can go through this whole thing where I say 0.01 times y of t plus delta t minus y of t all over delta t, yada, yada, is equal to 4, right? I can go through that whole process. If I go back and I look and I kind of, see that this guy matches the same form as what I was using before, I can end up saying that y of t plus delta t is equal to a1 x of t plus a2 y of t. And I could go back and I could figure out a1 and a2 are some constants that depend on all that junk. The 0.01s and the delta t's and all that kind of good stuff. Okay. So this is what I said. Okay, well, at t equal to n times delta t, this guy is y of n delta t plus delta t, a1 n delta t plus a2 y of n delta t. And we said I don't need the delta t's. So I can just say this guy is y of n plus 1 equals a1 x of n plus a2 y of n, like that. Now, how can I code that up? How could I write that in code? Yeah. How could I write that in code? Do a for loop, right? I'd have to define, so the thing what's the one thing here that I haven't told you? I've told you this tau value was 0.01. I told you my input was the number 4. I gave you an initial condition. What did I not give you? Well, I didn't, so n is just, n is going to start at 0, right? And it's going to go until whenever you stop. What did I not tell you? You got a question? Delta t. Yeah, I didn't tell you delta t. That's something I got to choose. Again, for the homework, current homework, number 5 there, I said I told you what to choose, I think. All right. On the project, you're going to have to make those choices yourself. All right. So we'll talk more about that next week. How do I make a choice like that? Yeah.
On my first day, talked about there was an equation when, since this is discrete, there's a way to make delta t like more accurate, instead of just putting like 1, 2, 4. Is that all in this thought?
Yeah, there's a theory to sort of the minimum choice that'll work. Which is a little bit more formal than it really needs to be. The real question is I know what it's going to look like here, right? So I just got to make sure that I choose a value that's small enough that it looks right. Now that sounds very informal, but it's actually not that hard to do. You make a really big number, you know, let's say I make it too big. Well, then I'm going to start out here and I'm going to end up here. And you know that's not right. And in fact, it's going to look all kinds of crazy. It's going to overshoot. It's going to do some weird stuff if I do that. All right. So I got to make it small enough. So next week we'll talk more about this idea of small enough. For now, I just want to get you to just sort of familiar with the concept, right? So I can do a for loop. All right. So here's how I set this up. I have my initial condition here, 10. Got my tau. I chose delta t equal to tau divided by 100. I'll talk about why that seems like a reasonable choice to me later. And then I got this A1 and A2, right? So I can go back and I can see where I came up with that delta t over tau and that 1 minus delta t over tau. And here, what did I do? Well, I created a y vector, which was all zeros. Okay. And then I said x is 4 times 1 size of t. So what does 1 size of t do? Again. Yeah. Yeah, vector of ones, it's the size of t, right? And I multiply it by 4, so yeah, it's a vector of 4s at that point. So here's my for loop. My for loop is implementing that equation. All right, now tell me more about my for loop there. So I loop from n equal 1 in steps of 1 to length of t minus 1. Okay. Let's check what's going on here, right? So if n equal 1, meaning I'm doing a logical check to see if n is equal to 1, I say y of 1 equals y underscore 0. What am I doing there? Yeah, I'm setting my initial condition. The first point is going to be equal to my initial condition. And then I'm going to say the next value is equal to whatever I have now plus some weighted version of my input, x. I'm basically just implementing this equation. Now, the thing that you may not like here is MATLAB, of course, numbers its arrays from 1. Right? So I said y of 1, whereas basically if you look at my math here, I would have said y of 0 is my first point, right? But because MATLAB starts from 1, it's off by 1 point, okay? Now, we said the graph should look like this right here, all right? So if I plot it, it does. All right, now what I actually plotted here is what I tell you to do in the homework, right? Where there's 2 graphs right there, right? So I actually plotted the exact solution and what I'm calling the approximate solution. In other words, what we just did here is not the exact solution, it's the approximate solution, right? And I plotted the 2 on top of each other, but they're pretty darn close. All right, now what I plotted here is exact minus approximate. Right, so there's the difference. I can kind of see, you may not be able to see it from where you are, but you know, when I look at my screen, I can see a little separation happening in there, right? And that's, you know, I can see that the difference between them maxes out at about 0.011, which, you know, given the amount of change here, you know, that's a relative error, 0.011 divided by 5 at that point. You know, it's on a percentage basis, that's pretty small. How can I make that error get better? In other words, by better meaning, how can I make the error get smaller? Yeah, change my delta t. In which way? Bigger or smaller? Well, I want my delta t to be smaller, right? I want a much smaller value. I'd have more samples, right? But I'd want my delta t to be, in other words, my jump between points should be a smaller and smaller value. In other words, I'm getting closer to continuous time. I'm making Newton happier, right? I'm making that limit as delta t goes to 0 smaller. So here's what I did. So this is what I had originally. I chose my delta t to be tau over 100. Here I chose it to be tau divided by 10,000. Okay, now first you might look at that and go, well, that looks worse. One thing MATLAB does, which is pretty annoying, it has that times, sometimes it'll do that times 10 to the minus third up there. Like boop over here, I think you sent me a DM the other day where you had like 0. So you showed me a number that was 10 to the 9th times 0, you know, plus j times like, you know, something, I don't know what it was, something like that. And I was like, what's your real part? You're like 0. If you actually look at it, it's not 0. All right, because it's actually, you know, if I said what's the real part of that number, I would probably see heck, that it was like 10,000 or something like that. It's just being dwarfed by the other one. So MATLAB has this really, this is very annoying. But if I look at this guy here is that maximum error looks like it's 1.1 times 10 to the minus 3, whereas here it's 1.1 times 10 to the minus 2. So it's seems like it should be different than that. Maybe my time step's 1,000 here, right? Either way, what I've done is I've made it smaller. Okay, I made the error smaller by making a smaller jump. And what's the trade-off? Well, the trade-off is what's good enough, right? And because I could keep making it smaller and smaller, the question is the error small enough, right? If I had shown you this, if I hadn't even plotted the exact over it, you would never have known, right? I could have just fooled you with that. Okay. So that's the important thing, is how much error can you really accept? So we'll talk more about how I make that choice, because that's important in controls and stuff like that. I've seen control systems where we've designed them and that we totally goofed up that number and the system starts to oscillate. So this motor that's supposed to go from here to there, just make a nice spin, starts going because you've chosen the wrong value. All right. So, all right, we'll talk more about this problem, but this is enough to be able to finish problem 5 on the homework. What's up?